Chapter 1.6, Inverse Functions. So definition, two functions f of x and f inverse of x. So this is f inverse of x are inverses of each other if the domain of f is the same as the range of f inverse, and the domain of f inverse is the same as the domain of f. So essentially, the domain and range are switched for f of x and its inverse. Okay, inverse functions undo each other, and when they are composed with one another, they are equal to the identity function x. So there was an example in the last section where we found when you compose two functions, it equals x. So in other words, if we have f and g, just be two functions such that f composed with g of x is equal to x for all x in the domain of g, actually I should put comma, and at the same time, g composed of f of x is equal to x for all x in the domain of f, then this means that f and g are inverses. So one thing that's important is that when you take the composition of two functions and you get x, it has to be both directions. So f composed with g of x has to be x, and g composed of f of x has to be x. Both must be true. So if you're asked to show it, you must show both ways, both equal x for them to be inverses. So we're gonna do some examples where we're proving that they're inverses. So in this example, we're gonna take f of x and g of x and prove they're inverses. So we must show that f composed of g of x equals x, and g composed of f of x equals x. So let's start with f. So f composed with g of x is equal to f of g of x, which is equal to f of g of x, they told us was 1/2 x plus 3. So that means that I'm going to take this guy, and in the f of x function, wherever there's an x, I'm going to replace it with the 1/2 x plus 3. So this is going to equal 2 times 1/2 x plus 3, and then minus 6. I took the x and f and replaced it with g. So to simplify, I'm going to distribute the 2. 2 times 1/2 x is just x. 2 times 3 is 6, minus 6. So this just becomes x. So to do the other direction, so g composed of f of x. So that's going to be g of f of x, which is equal to g of f of x was 2x minus 6. So I'm going to take 2x minus 6 and substitute that in for the x in g. So instead of 1/2 times x, it's going to be 1/2 times, excuse me, 2x minus 6 plus 3. Distribute the 1/2. 1/2 times 2x is just x minus 3 plus 3, and then the -3 and 3 cancel, and you just get x. So what this means is we just showed that f composed of g of x equals x, and we showed that g composed of f of x is equal to x. So therefore, f and g are inverses. Now in class today, I told you guys that you guys can use the symbol if you want. This just means therefore. And then whenever you're done with because it's kind of like a proof for showing something is true, a way that we in that typically is just drawing a square and then just filling it in. You can do that if you want. You don't have to though, but it's kind of cool. All right, let's try another one. Show that f of x is 2x cubed minus 1, and g of x is the cube root of x plus 1 over 2 are inverses. So again, we need to show that we must show that f composed with g of x is equal to x, and g composed of f of x is equal to x. So let's start with f. So that's going to be f of g of x, which is going to be f of g of x is the cube root of x plus 1 over 2. So we're going to take this and plug it in for x in the f of x function. So this is going to be, it's 2x cubed, so 2 times, we're going to replace it with the cube root of x plus 1 over 2, and then we're going to raise that to the third power minus 1. Whenever you have the cube root of something raised to the third power, these are inverses of each other. So if you cube a cube root, the radical and the power cancel. So you're just left with what's on the inside. So 2 times x plus 1 over 2 minus 1. 2 times this fraction is going to become 1 because 2 over 2 is 1. So this 2 and this 2 are going to cancel out. So we're just going to be left with x plus 1 minus 1, which is x. Now to do the other direction, so let's do g composed with f of x. So that's going to be g of f of x, which is going to be g of f of x this time was 2x cubed minus 1. So I'm going to take that and plug that in for the x in g. So here, notice that it's on the inside of the cube root and it's on top. So I'm going to rewrite this, but instead of writing x, I'm going to put a parentheses and then the entire f of x function. So this is going to equal the cube root of parentheses 2x cubed minus 1 plus 1 over 2. Simplifying the numerator, the -1 and +1 will cancel, leaving us with the cube root of 2x cubed over 2. These 2's will cancel out, leaving us with just the cube root of x cubed, which is just x. So f composed with g of x is equal to x, and g composed with f of x is equal to x. So therefore, f and g are inverses. Okay. Verify that these two functions are inverses. So this one's a little bit trickier. So we need to show both directions again. So let's start with f. So f composed with g of x is going to be f of g of x. So it's going to be f. Actually, I messed up already. This was h. So I need to change this to h. F of h of x they gave us was 5 over x plus 2. So I'm going to plug this in for x and f. So if you notice, the x is in the denominator. So I'm going to replace this x with a parentheses and then all of the h of x function. So it's going to equal 5 over parentheses 5 over x plus 2 minus 2. So before we freak out, because yes, this looks weird, just think about it. Positive 2 and negative 2 cancel out. So I'm left with 5 over x. So this is what we call a complex fraction because we have a fraction inside of a fraction. So all this is saying is 5 divided by this fraction. So what we can think about is I want to divide fractions. So the rule for fractions is you're going to change this to multiplication and then do the reciprocal of this guy. So I could actually change the 5 to 5 over 1. And we're dividing that by the 5 over x on the bottom. So we're going to change this to 5 over 1 times x over 5. And then I have a 5 in the numerator and a 5 in the denominator, so I can cross cancel these. So this cancels with this 5. So I'm left with just x over 1, which is x. So now we need to do the other way. So h composed with f of x is going to be equal to h of f of x, which will be equal to h of 5 over x minus 2. So wherever there's an x and h, I'm going to replace it with the 5 over x minus 2. So this is going to equal 5 over x minus 2 plus 2. So I can think about this the same way as the last one. I have a complex fraction. So I'm going to take this guy and multiply it by the reciprocal of this fraction. So this is going to equal 5 over 1 times x minus 2 over 5. And then all of that plus 2. Cross cancel these. So I'm just left with x minus 2 divided by 1, which is just x minus 2. Plus 2, which is x. So we know that f composed with h of x equals x. And we showed that h composed with f of x is equal to x. So therefore, f and h are inverses. Okay, we should have seen this last year, but just some review. So if you know that the point a comma b, so any point that you know exists on the graph of f, then for the inverse, the point b comma a, so you take the inputs and outputs and they switch, and that point will lie on the graph of the inverse. So then we can determine that this by the graph of the f inverse is a reflection across the line y equals x. So in other words, if this is your f of x function, and this is your f inverse of x function, the graph, if we draw this diagonal line y equals x, basically these graphs are mirrored from each other across this diagonal line. So we can use a graphing calculator to tell whether two functions are inverses by just graphing them essentially, because then we can see also that every input and output of one function is a reverse. Because remember, talking about this at the beginning of the notes, the domain and range of f and its inverse are switched. So example 4, verify that the functions f of x is x minus 5 over 2 and g of x is 2x plus 5 are inverse functions of each other graphically and numerically. So you guys have a couple problems like this. I think one of them is on your worksheet and some of them might be in your homework. But basically when it says numerically, I just want you guys to prove to me that if I plug in some inputs and outputs, that they are switched between the two functions. So if these are inverses and they tell us that they're inverses, that means if I make a table for this function, just picking a couple of points, that means that if I plug the same points into here, we should see that the inputs and outputs are switched. So it doesn't matter which one I pick, but because this is a fraction, I feel like this one might be easier to make a table for. So all I'm going to do is I'm going to pick 3 x values, plug them into this function to get y's first. So to show that these are inverses numerically, I'm going to start with g of x is the 2x plus 5. So just to build a table, I'm going to try to make my life easier. So I'm going to pick like 0. If x is 0, then the output's going to be 5. If x is 1, 2 times 1 is 2, plus 5 is 7. If x is 2, 2 times 2 is 4, plus 5 is 9. Okay, so now we're going to test to see if the inputs and outputs are actually switched. So this means these are the outputs for G. So that means if I plug these numbers into F, the outputs should be the inputs of G. So in other words, 5, 0 should be a point for this guy. 7, 1 should be a point for this guy, and so on. So let's try it. So if I now do the same thing for f of x and make a table. So let's plug in 5. Because if these truly are switched, then I should get 0 back. So if x is 5, 5 minus 5 is 0. 0 divided by 2 is 0. If I plug in 7, 7 minus 5 is 2. 2 divided by 2 is 1. If I plug in 9, 9 minus 5 is 4. 4 divided by 2 is 2. So it looks like that these two functions are inverses numerically. So we can say that since we can see the inputs and outputs are switched, for multiple values, we could say that f and g are inverses. So then if I want to show it graphically, okay, I have these covered up because I'm going to show you guys these in class, but I'm going to now change my screen to show you guys the graphing calculator to show you guys what it looks like. So go to y equals, and we're going to type in the x minus 5 over 2. So if I want to do a fraction, I can do alpha. And then if you see it, this little fraction guy's in green. So if I click on that, x minus 5 over 2. And then the other graph, we're going to do 2x plus 5. And if I hit graph, it's kind of hard to tell. So I'm going to actually zoom out because I feel like this is too zoomed in. So I'm going to hit zoom 6, and it's going to reset the window for me. Okay, that looks better. So if these are inverse of each other, that means that they are reflections across the line y equals x. So if I go back to y equals, in the third equation, I'm going to change this to x, because then we should see that the these graphs are mirrored across this line, and it looks like it. So this is another way you can tell that two graphs are inverses, because if I take this blue line and flip it across diagonally this way, it should land on the red line. So that's another way we could show it, is by using a graph, or you could graph this by hand. But I just want to show you guys how you guys can do this. You guys won't have to do this on a test, but that's basically just algebraically one of the ways to prove it. So let's go back to the iPad. All right, definition, one-to-one functions. So this definition did come up last year in Math 3. But I'm gonna give it to you guys again. So to have an inverse function, because some functions don't, a function must be one-to-one. So what that means is no two outputs can have the same input. Actually, I wrote this completely wrong. So let's start this over. So if you're watching this, I apologize. I'm going to change it right now. So that means that no two elements in the domain of F can have the same output in the range of F. Okay, so for one-to-one, a function's one-to-one when for A and B not the word B in its domain F of A equals F of B implies that A equals B. So in other words, if two Y values equal the same, then that means that the inputs must be the same. And if they're not, that means that it's not one-to-one. So therefore, the big conclusion of this is a function F has an inverse function F inverse if and only if F is one-to-one. So if a function is not one-to-one, then it doesn't have an inverse. So one way that we could tell it's one-to-one is by doing the horizontal line test. So the graph of F is one-to-one if and only if any horizontal line drawn on the graph of F does not intersect the graph more than once. So it's kind of like the vertical line test in that you want to draw now a horizontal line. And if it touches twice, that means it's not one-to-one, which means that it doesn't have an inverse. So if the horizontal line test fails, that means no inverse for that function. So the classic example that you guys should have saw in math 3 last year is x squared. The graph of a parabola, a bunch of y's, y values have multiple different inputs. So like f of -1 is equal to 1 and f of 1 is equal to 1. So if I draw a horizontal line through y equals 1, there's the horizontal line crosses the graph twice. So that means that x squared is not 1 to 1, which means that x squared does not have an inverse function. So there's also another way to test this, and it's the fact that if a graph is always increasing over its entire domain, then it's 1 to 1. Or if f is always decreasing on its entire domain, then it's 1 to 1. So like if you look at x squared, it's decreasing from -infinity all the way to 0, and then all of a sudden it's going to start increasing at 0. So therefore, because the behavior changes, that means that at some point it's not going to be 1 to 1 anymore. Okay, so verifying a function is 1 to 1. So is the function f of x is equal to the square root of x plus 1? Is that 1 to 1? So algebraically, so we can do this without graphing it first. So if it's 1 to 1, that means that f of a equals f of b implies, so this symbol means implies that a equals b. So we're going to plug in a into this instead of equal to plugging in b. So instead of writing the square root of x plus 1, I'm going to say the square root of a plus 1, and that's supposed to be equal to the square root of b plus 1. So then if I want to try to be clever, the plus 1 and plus 1, I can subtract 1 from both sides, and then those cancel. I'm left with just the square root of a is equal to the square root of b. And then if I want to get rid of the radical, if I square both sides, and then I get a is equal to b. So because I plugged in a into this function and plugged in b into this function, and I was able to algebraically manipulate it to get a equals b, that means that therefore the square root of x plus 1 is indeed 1 to 1. Okay, but we can also plug this into our calculators and see what the graph looks like. So square root of x plus 1 looks like this. It's always increasing. So that means that any horizontal line we graph is only going to hit the graph only once. So this does pass the horizontal line test. So therefore, because it passes, f is 1 to 1, and it does have an inverse function. Okay. We're going to review now how to find the steps to finding an inverse function. So another thing you guys talked about in math 3. So the first thing you're going to do is you're going to use the horizontal line test to determine if it does have an inverse. Okay, so you can either do that graphically or algebraically. Then replace f of x with y. Switch x with y. Solve for y. Then once you're done, change y to f inverse of x. And then, and this is something that you guys will need to do on your tests, is to prove they are inverses by showing that the composition is equal to x. So f of f inverse of x equals x, and the reverse, f inverse of f of x is equal to x. So we're going to practice doing that for a few examples. So find the inverse function of f of x is equal to 5 minus 3x over 2. So we can plug this into a calculator and verify this, that this does pass the horizontal line test. So I'm going to skip that part, but I want to practice with you guys how to do the steps to find the inverse. So the first thing you're going to do is you're going to replace this guy, change this to y is equal to 5 minus 3x over 2. Second step is to switch x and y. So x is equal to 5 minus 3y over 2. And now the goal is to solve for y. So I'm going to multiply both sides by 2. So you get 2x is equal to 5 minus 3y, because these cancel. Subtract 5. So 2x minus 5 is equal to negative 3y. Divide both sides by negative 3. Now you could rewrite this in slope-intercept form, but we don't necessarily need to because we're not graphing it, and you're not asked to find the slope or the y-intercept in this problem. So you could just leave it like that, and that's fine. So we get y is equal to 2x minus 5 over negative 3, but we need to rewrite it as its inverse. So f inverse of x is equal to 2x minus 5 over negative 3. So this is the inverse. So then what you'll have to do is prove they are inverses by doing the composition. So we're going to verify. So f composed with f inverse of x is f of f inverse of x. So f of f inverse of x was 2x minus 5 over negative 3. So we're going to take this and plug this in for x in f of x. So that's going to equal 5 minus 3 times 2x minus 5 over negative 3. And then all that's over 2. I have a negative 3 times something with negative 3 on the bottom. So these negative 3s are going to become just 1. So they cancel. So I'm just going to get 5 plus 2x minus 5 all over 2. On top, the 5s cancel. So you just get 2x over 2, which is x. Then, to do the opposite, f inverse composed with f of x is f inverse of f of x. So it's going to be f inverse of f of x was 5 minus 3x over 2. So I'm going to take x and plug that in. Sorry, take this function and plug it in for x and the inverse. So you're going to get 2 parentheses 5 minus 3x over 2 minus 5 all over negative 3. These 2's will cancel. So you're left with 5 minus 3x minus 5 all over negative 3. 5 minus 5 cancels. So you just have negative 3x over negative 3, which is just x. So this is how you prove that they're inverses. All right. Finding the inverse of x cubed minus 4. So same idea. First thing you do is replace this with y. And then switch x and y. So you're going to get x is equal to y cubed minus 4. Now you're going to solve for y, so add 4. X plus 4 is equal to y cubed. Then we need to cube root both sides. So we're going to get y is equal to the cube root of x plus 4. And then just replace that y with f inverse. So f inverse of x is equal to the cube root of x plus 4. And then the last thing you'll need to do is prove it. So this one's pretty easy. A little less messy than the last one. So f composed with f inverse of x is f of f inverse of x. So we just found that the inverse was the cube root of x plus 4. So plugging that in into f. So that's going to be parentheses, the cube root of x plus 4 cubed minus 4. The cube root and the power of 3 are going to cancel out. So you're just left with x plus 4 minus 4, which is x. F inverse composed with f of x is f inverse of f of x. So it's f inverse of x cubed minus 4. So this is going to get thrown in for x in the inverse we just found. So it's going to be the cube root of x cubed minus 4 plus 4. So on the inside, the negative 4 and 4 cancel out. So you have the cube root of x cubed, which is x. All right, last example. Find the inverse function of f of x is equal to the square root of 2x minus 3. So this one's going to start off the same. Replace f of x with y. Switch x and y. So you're going to have x is equal to the square root of 2y minus 3. So if I want to solve for y, I need to square both sides to get rid of the radical. So x squared is equal to 2y minus 3. Add 3. So x squared plus 3 is equal to 2y. Divide both sides by 2. X squared plus 3 over 2 is equal to y, which means that f inverse of x is equal to x squared plus 3 all over 2. Okay, now, one thing we have to pay attention to is the fact that the domain and range of these guys have to switch. So if we just looked at this because it's quadratic, we would say that the domain is all real numbers, but that's not true for this guy because we can't take the square root of a negative. So if we graph this, we would find that the domain of this guy is going to be 3 over 2 to infinity, which means that the range, if you graph this, was 0 to infinity. So remember, the domain and range of f with its inverse switch. So that means that the domain of this guy is going to be the same thing as the range of its original function. So when we write our final answer, what we have to say is that for this function, the domain is only true for when x is greater than or equal to 0. So this is our inverse function in this problem. So to go ahead and verify. So I'm going to do this direction first. So that's going to be f of x squared plus 3 over 2. So plugging this in for x. So we're going to get the square root of 2 times x squared plus 3 over 2 minus 3. These 2's cancel. So you get the square root of x squared plus 3 minus 3, which is the square root of x squared, which is just x. Then doing the other way, we're going to have f inverse composed with f, which is f inverse of f of x. So it's going to be f inverse of the square root of 2x plus 3. So I'm going to take this guy and plug it in for x in the inverse we found. So this will equal parentheses the square root of 2x plus 3 squared. I already messed up. This should be minus 3, which makes this a minus 3. And then plus 3 all over 2. The radical squared will cancel out. So I'm left with just the inside. So 2x minus 3 plus 3 over 2. Negative 3 and positive 3 cancel. So you get 2x over 2, which is just x. And that is the end of 1.6. And this is the end of chapter 1.